Okay, here's the solution to problem 2. In problem 2, we have a very large sphere that is, if you like, think glued to the ground down here, so it can't move. But on top of that sphere, we put another sphere, and we release it from rest. So at the top here, the velocity at t equals 0, or in other words, v sub 0 is 0 at t equals 0. That thing is not moving. And then a flea sneezes on it and it starts to roll down the sphere, and it rolls down the sphere, and it does so without slipping on the sphere. And at some point, this small sphere will lose contact with the sphere, and then of course it will move in a nice parabolic trajectory down to the ground and smash into the ground down here somewhere. But what I'm interested in is what angle does it fall off at? And so the way I asked you to solve this problem is to do it in 2 steps. First, figure out an expression that would give me the instantaneous velocity, which would of course be tangent to the circle. I want to know this instantaneous velocity here when it's moved through some angle theta. Okay? So the way I'm going to do that is I'm going to use energy conservation. So I need to write down the initial energy at the top and equate that to the total mechanical energy right at this point here when it's gone through an angle theta. So to do that, I need to be able to calculate the initial kinetic energy and the initial potential energy. Well, the kinetic energy is easy to start with because this thing starts from rest, so it has no kinetic energy at all. The final energy definitely does have kinetic energy in the final state. We'll talk about that in a minute. And some potential energy. Okay, so now we have 2 things to deal with: how to calculate that final kinetic energy and how to calculate the potential energy in this problem. And the way I will do that is I will pick a coordinate system for potential energy that is right 0 at the center of this sphere. So here is y equals 0. And then I think you can see that the initial potential energy will just be m times g times capital R, the radius of the big sphere, plus little r, right? Because that is the height that this center of mass is above this origin. So that is y initial. Then to calculate the potential energy in the final state, I need the distance that I will outline here in kind of green. I need this distance right here. Right? But I think you can see that that distance isn't so hard to calculate, because if we use a little trigonometry, I think you can see that this side of the triangle is adjacent to the angle theta, and the hypotenuse is right here. That's little r plus big R. This green is a little bit hard to see, so let me make it a little darker. Okay, so this distance that we're interested in, I think, give yourself a second and see if you can figure that out. Okay, you should have found that that distance is r plus little r times cosine theta. Okay, I think we're ready to put in the pieces. The only thing we have to talk about here is this final kinetic energy. When the sphere gets to this point, after rolling through an angle theta, it has 2 terms in its kinetic energy. It has its center of mass kinetic energy, and it has a rotational energy of 1/2 I omega squared. And the constraint for rolling without slipping tells us that omega is v over little r, because it's the radius of the sphere that's rolling on the surface that's relevant to calculate the angular velocity omega. Okay, so putting all of this together, equating the initial total mechanical energy to the final total mechanical energy, gives me the following equation: mg times big R plus little r equals 1/2 mv squared. Now I will substitute this expression here for omega right in here, and I'll collect terms, and I think you can see that I'll get a 1/2. I will get an I divided by little r squared, and that'll also be then times v squared. And then I have to add to this one more term, which is the potential energy, m times g times r plus little r times cos theta. Alright, so now I'm going to erase a bunch of stuff here and rewrite that equation so it looks a little easier to follow. So give me a second. Okay, so now I've rewritten our energy conservation equation. I can simplify a lot of things. I notice on the left-hand side here I've got an mg little r plus big R, and I've got almost the same thing here, so I'll bring that term on the right over to the left, factor out the obvious piece, and I think you can see that what I'm left with is mg times big R plus little r times 1 minus cos theta. And on the right hand side I factor out a 1/2, then I get a m I over r squared for a sphere is 2/5 m. And that's times v squared. Okay, so we now have an equation that allows us to calculate v squared. And if I solve that, then what do I get? I get the whole left-hand side. Notice that there's an m. Let me cancel out a couple terms, one term here. There's an m here, and there's an m in this term. If I can't divide out by m, that leaves me with a 1 there, and divide out by an m there. And then if I multiply both sides, or let's see, let's simplify the right-hand side. So let me actually erase this v squared for a second. Do one other step. The right-hand side I can write as 1/2, and then I have a 1 plus 2/5 times v squared. Well, that's easy. 1 plus 2/5 is 7/5. So this looks like 7/10 v squared. Okay, so now if I combine that, if I solve that for v squared, then I think you can see that v squared will be 10/7 times g big R plus little r, and then times 1 minus cos theta. Alright, so there's the first piece. We've now got a relationship for v squared. Okay, the second piece I wanted you to do was to give me an equation that describes the normal force as a function of theta. And for that, I'm going to use Newton's law. So let me draw on here the forces acting on this sphere. There are two of them only. There's gravity, mg, and there's a normal force that is exerted by this contact here, and it's exerted along the radius, and that force is n, and I drew that a little bit too long, so let me undo that and draw it a little bit more realistically short, something like this. It has to be shorter because the normal force has a component that is only this big, and that has to outweigh, the normal force has two components, right? And it's this inward component here that keeps the thing moving towards the center of the circle. Alright, so I think you can see with a little bit of geometry that if this angle is theta over here, that the angle theta also appears right, let's see, if that's theta, this is 90 minus theta, but this is a right angle, so this angle here is also theta. Okay, so the little yellow line here pointing to this vector, that component of mg is therefore mg times cosine theta. Okay, so now Newton's law applied to that sphere. What is Newton's law? Sum of the forces in the radial direction is the mass of that sphere times the acceleration in the radial direction. And acting towards the center of the sphere is mg cosine theta. Acting away from the center of the large sphere is the normal force, n. And that must equal the mass of the sphere times its acceleration towards the center, which is v squared over r. And the r is the radius of the path of the center of mass, and that r is little r plus big R. And that's a subtle but important point. Okay, so now we have an equation that we could solve for n at any angle theta. Okay, so here's the key observation, that the little sphere loses contact when the normal force vanishes. So when the normal force here goes to 0, then the sphere loses contact. And at which point we have the following relationship. mg cosine theta is mv squared divided by little r plus big R. Notice the mass drops out, and now I can solve this for v squared, and I get v squared is g times little r plus big R times cos theta. So interestingly, that equation for v squared and this equation for v squared, they're different, but since they're both equal to v squared, we can equate the two expressions to each other. And so now, let me make some space here, and now we're just going to solve the remaining part of the problem. I'll get rid of our original figure. And let's solve this system. Okay, so here we go. We must have that 10/7 g times big R plus little r times 1 minus cos theta must equal g times little r plus big R times cos theta. And tons of stuff cancels out here amazingly. So in fact, what cancels? G times little r plus big R cancels g times little r plus big R. And now we just have a very simple equation left. We have 10/7 minus 10/7 cos theta equals cos theta. This is simple to solve. 10/7 must equal then, let's see, we bring this term to the other side, and we get 10/7 plus 1, which is 17/7 times cos theta. And now I can solve for cosine theta. I multiply both sides by 7 over 17, and I get on the left-hand side 10/17 when all is said and done. So now all we have to do is the inverse cosine of 10/17, and that is equal to theta. If you plug that into your calculator, you get 53.97 degrees, and that is the final answer for theta.